right, good. So here we go. Let's see, real quick check. Yeah, okay, good, we're recording. Okay, so last time we just barely scratched the surface of section 2.3. The only introductory comment I made was about the fact that there are actually multiple kinds of derivatives that you have to kind of be on the lookout for in multivariable calculus. So you can't think of it as, oh, well, there's the derivative. There's several of them, depending on how you count. So the reason we use the word derivative to apply to all of them is because they all have an important characteristic in common, and that is they all, in some way or another, appropriate to the circumstance and how they individually work, they all relate input changes and output changes in some way or another. So think about single variable derivatives, of course. Again, is a relationship between input changes and output changes. You might say the single variable derivative is a fraction. It's output change over input change, something like that. Right? Okay. All right. So here's our first derivative now that we're going to talk about in this course. It's called partial derivatives. Some of you may have seen these before. They are useful. We like them because they're easy to compute. We like them because they're familiar. They are going to be easily connected to single variable derivatives that you're already familiar with in several ways. And the other reason I start with partial derivatives is because the book does, and I emphasize that that's actually a pretty big deal. If it was entirely up to me, I probably wouldn't. I think there's a case against starting with partial derivatives. And here's that case. Certainly when you leave this course, when someone asks you what's the single most natural point of view on derivatives, I really hope you won't think it's partial derivatives, because I don't think that is fundamentally deep down the most important basic point of view on derivatives. Now don't get me wrong, partial derivatives have an important role to play, but don't hang your hat on this point of view. This is a good first effort, I think, is a nice way to think about it. Okay. All right, so that said, here we go. Here's how you compute partial derivatives. It's a two-step process. Step one is hold all of the variables constant except for one. One of the variables you will not hold constant. So keep in mind, presumably we have a multivariable function here. That means there's lots of input variables. We're going to identify one of the input variables to remain a variable, and all of the others we're going to just take as fixed, take as constant, and they're not allowed to change. Okay, now, if you think about it then, we started with a multivariable function because there were multiple variables, but now most of them aren't really variables anymore, at least for the purposes of this computation we're doing. And if you have a bunch of variables, but most of them are no longer variables, there's really only one actual variable left. So the point is the result of step one is to produce a single variable function. Math219 style, just a plain old regular single variable function. And so step two, take the usual derivative of that resulting single variable function. Oh, this is what a partial derivative is, and we have some notations for it. You'll probably kind of sort of recognize this in some sense. It looks a lot like, anyway, the Leibniz notation for Calc 1 derivatives. Do notice, however, and this is important, that little symbol right there, that is not a D. Kind of looks like a D. I think it's reasonable to speculate it was probably designed to look like a D, but it's very importantly not a D, and you can't use a D instead, and it's not equivalent, and not a D. So be careful about that. Also, commonly misunderstood, a lot of people think it's the Greek letter delta. Nope, it is not. Greek letter delta is just that little bit different in the way it kind of flops over to the right on the top, and the partial symbol does not do that. Okay, so heads up about that. Another notation to keep in mind is this one right here, where the subscript is the indication of which of the several variables you're going to be taking the partial derivative with respect to, and which is the one variable that is not taken to be a constant. Anyway, just another alternative, yeah.
Where does that symbol come from?
That's a good question. Historically, I actually don't know. I would suspect somebody made it up. I'm not sure. This symbol does get used in other circumstances, but when it does get used, my understanding has been that it gets used in these other circumstances because it actually is kind of a partial derivative. And it can be connected to the idea of a partial derivative in some way or another. Okay, so let's do an example. We're going to do the two-step process. Compute a partial derivative. Here we go, starting with taking a partial with respect to y of this great big monstrosity right here. And yikes, right? That's a scary-looking function. It's got three factors, so I feel like I'm going to be using the product rule multiple times. One of them is a composition that has a product inside of it. Right, this looks like it's going to be tedious. It's not. It's actually a really easy one. Key point is you got to remember y is the function. That means, y being the function, that y squared is a function. But x is a constant, and that means that e to the x is a constant. And x being a constant, and don't forget z is a constant too, and that means that all of this is a constant. That means that all of this is all just a great big constant, right? Everything except for the y squared. It's just a constant. Multiplicative constant. You can think of this function then, as far as this one partial derivative is concerned, you can think of this as being k times y squared. And that's an easy derivative to do, right? The partial derivative, or the derivative of y squared with respect to y, I guess I'll say, is 2y. Nothing to it. Multiplicative constants stick around. You can move the terms around if you like. I mean, most of the time it's considered standard to take numerical factors like this 2 and put it in front. Whatever, that's all just trivialities. But the derivative, the differentiation here is a freebie. Everybody see how that works? Okay. All right. Next example. Let's look at this one here. And again, kind of scary looking at a quick glance, but then you notice that, wait a minute, we're taking a partial with respect to x. That means x is a variable. That means that this expression right here is a function. Okay, sure, but all the other variables are constant. That means that this y that I see right here, that's a constant. That means that this whole exponent, in fact, is just a great big constant. So at a quick glance, it might have looked like, this is a function to the power of a function. We're going to have to do like logarithmic differentiation or something like that. But no, just a power rule. This constant exponent, you do the usual, you bring it down to the front, you subtract 1, just regular old power rule. Nice and easy. Does that make sense to everybody? Almost seems too good to be true. That's one of the reasons we love partial derivatives, is they're so easy to compute. I propose, in fact, that partial derivatives of multivariable functions are arguably easier to compute than single variable derivatives. Because ultimately you're just doing single variable differentiation, but in advance you get to just ignore huge parts of the function and just treat them as constants. Wouldn't that have been nice back in your Calc 1 class to I'm just going to treat all this over here as a constant. Right? So super easy to compute. Last quickie example. Again, it kind of at a quick glance appears that we have a function to the power of a function. But nope, z is our variable. That means x and y are constants. That means that this whole base down here is just a constant. This is not a hard function. This is a basic exponential. This is k to the power of x. K to the power of z. And we have an old rule from Calc 1 as to how to compute those derivatives. Okay, so nice and easy. Everybody on board? Okay, now currently lacking. We have a definition for partial derivatives. We have a notation. We have some examples under our belt. And we have, as of this moment, no reason to believe that there's anything useful about partial derivatives, right? If you're going to use something, it needs to either be directly relatable to some physical concept, or it needs to have some geometric interpretation, and that geometric interpretation is the opportunity for that to connect to something you're eventually going to actually care about, some sort of application or something, right? And as of the moment, we don't have any. So that is the next thing we need to do, is to think about the geometric interpretations. And now I'm going to flash back to a point y'all have heard me make many times over the last few class meetings, and that is that if you want to interpret, if you want to do calculus in relation to a picture, it depends very, very dramatically on what kind of a picture are you looking at, right? So we're going to make some interpretations of partial derivatives. We're going to get one interpretation in terms of, what do partials look like on graphs? And then when we ask, what do partial derivatives look like for level sets? Totally different. Completely different answer. Right? So we will start with graphs, mostly because it's the most kind of familiar and relatable. But this is not the only interpretation. And again, please don't paint too broadly in your mind, what we're about to show. That what we're about to do here is only for graphs. Okay. Alrighty, so with that in mind, starting with a graph. As you'll notice here, this is a graph because we have the value of this function f set equal to a new variable, z in this case. Right, so graph. Let's see here. You'll notice that you can see the domain R2, kind of, anyway, down here. XY plane in this three-dimensional picture. It's a little bit of an abuse, but it's good enough for our purposes. You can also kind of sort of see the target. I'm going to use Z in green because that's what makes it a graph. Right? So in some sense, kind of a domain down here, kind of a target there. Altogether, the graph lives in this weird three-dimensional space. It's not the domain, it's not the target. This is just this weird hybrid world that the graph lives in. All right, so what does a partial with respect to y look like on this picture? And I emphasize further, evaluated at this point AB. So we have to indicate where are we asking about the partial derivative. So in the domain, it's the point A comma B, at which I want to take the partial with respect to y. Okay, now, so I've laid out the question. I haven't started the answer. Is everybody on board with the question? Okay. All right. Okay, well, by the way, here's our graph. Right. And if we want to take a partial derivative, we have a two-step process. Remember, we're taking the partial with respect to y, which means y is going to remain a variable. Step one is to recall that we're going to set the other variables, just x. We're going to set the other variables to be constant. So as we compute this partial derivative, x is not allowed to change. Now notice that x is already a. So if it's not allowed to change, that means it has to stay at this value a, which means that geometrically speaking, as we fix x at that value a, what we're effectively doing is taking a cross-section of our graph with that plane. That's the plane x equals a. Everybody good? Okay, now, this plane, there's a couple different ways you could describe this plane. A lot of people would describe this as, well, this plane is perpendicular to the x-axis. That's a good point of view. Important to make that realization. But here's another way to think about it. This is a plane that points in the y direction. This is a source of confusion, right? So you got to make sure to keep it straight when you're taking a partial of a function of two variables. One of the variables is constant, one of the variables is a variable. The resulting cross-section plane, it's perpendicular to one of the axes, it's parallel to the other axis. It's really easy to get it kind of oopsed and backwards, and then you're going to get some dramatically wrong answers. So take the moment necessary to think through which variable is what, constant or variable, and therefore parallel or perpendicular to what. Okay. All right. Okay, now, looking at this cross-section, keeping in mind we started off with this whole graph, but x is not allowed to change, x is constant, so now we're really only looking above that line, which means we're really actually only interested now in that cross-section curve right there. And let's take a moment to think about, what does this cross-section represent? It's giving me heights, you might say, z, heights, and it's giving me those heights in terms of values of y, because y is the only thing it's allowed to change. X is fixed, right? So really, this curve here is height in terms of the variable y. It's vertical as a function of horizontal. This curve itself is a graph. This curve itself, in fact, is the graph of our new single variable function. So remember, the whole idea was we start with a function of two variables. We hold one of the variables constant to give ourselves a single variable function. This cross-section is the graph of my new single variable function. Okay. All right. Okay, and with that noticed, second step, given that we are looking at the graph of my new single variable function, step 2, taking the derivative with respect to y, means that as I go in the y direction, this derivative is just going to give me the slope of the tangent line. And that's what I have drawn here. Again, we have this curve. The derivative is the slope of that tangent line right there. So this is a nicely familiar result, right? I mean, calculus, Calc 1, derivative was the slope of the tangent line. Cool. Here, partial derivative is the slope of the tangent line. Okay, wait a minute. We do have to be a little bit more detailed about this. It's a specific tangent line. In fact, if you look back up here at our original picture, not only is there a tangent line to this surface at that point, there's kind of a whole tangent plane. There's a bazillion different tangent lines. So you can't just say the tangent line. There's so many of them. There is, however, only one tangent line in the y direction. Right, so as you're going in the y direction, there is exactly one tangent line to that graph. So, with that understood, partial derivative, slope of the tangent line to the graph, of course, in the indicated direction. All right. Now, you can probably speculate what would happen if we asked what is the interpretation of a partial with respect to x. You would be right. However, if you made the obvious speculation that the pattern would continue, right? Indeed, it does. Nevertheless, I think this is a really good exercise to think through. And again, you're not going to turn it in. You don't have to, but I think it's very healthy, learning experience to take all the pictures and arguments that we just made for the y partial and think through how would that argument have to be adapted if you're interested in an x partial. Draw all the appropriate pictures, think through all the relevant details, persuade yourself that this is actually correct. Everybody see what I'm suggesting here? All right. Okay. So now, reminder, we get a different geometric interpretation depending on what kind of a picture you're looking at. We now understand partial derivatives in the graph context. We move on now to trying to understand partial derivatives on other kinds of pictures. So, for example, one of my favorite, I would say my nomination for most underappreciated picture for a multivariable function, this literal picture. So, there's a partial derivative of slope on this picture. No, not at all. Slope of what? There is no shape, right, to even talk about a tangent line of. So we can't do that at all. So how am I going to make sense out of the y partial? I'm going to remind y'all that there are multiple interpretations of derivatives, single variable derivatives. Ultimately, of course, a partial derivative is a single variable derivative. And one of the things about single variable derivatives is you can use them as what you multiply by your input differential to get your output differential. I hope you all remember that a little bit of interpretation of single variable calculus. So where are these derivatives on this picture? Keeping in mind that we're taking a partial with respect to y, that means that x and z are both constant. X and z are not allowed to change as we entertain this y partial. That means that whatever the value of x is, it's fixed. Whatever the value of z is, it's fixed. And we can only move in the y direction because x and z can't change. Okay, so when I say the input differential, this dy, I'm going to use a different color, this dy, this input differential, I mean, how much did the only variable, y, the only remaining variable, how much did that only remaining input variable actually change? And multiplying by the derivative gives me the output differential, namely our linear estimate of how much the output changes. So again, you see we have the partial derivative understood as a relationship between input changes and output changes. Here's the input change dy, here's the output change df, and here's how the partial is a relationship between them. It's what you multiply by dy to get df in this picture. Everybody all right with that? Let me complain about this picture a little bit. This tells me what the partial derivative does, but it doesn't tell me what the partial derivative looks like. I can't point in this picture on the picture itself as to where the partial derivative is. And yes, that is disappointing. That is the nature of this picture. So again, it's tempting to say, well, phooey on this. I'd much rather deal with the graph where I have an actual shape on which I can talk about actual tangent lines and slopes. It's very geometrically satisfying. And who needs this nonsense right here? Answer, don't make apples and oranges comparisons. This picture that we drew here is for a function of two input variables. That is, of course, our upper limit for drawing graphs. I can't even draw a graph of a function with three input variables. So this unfair comparison of an easy task for the graph question and a hard task for the literal picture is not fair. The fair comparison would be this geometric interpretation of partials in this picture versus absolutely no intuition at all on the graph picture because the graph would be four-dimensional. So it's this or nothing in this picture. And between disappointing and nothing, you got to go with disappointing. So it's at least it's something. Is everybody happy? Everybody buy it? All right. Okay, moving along. What about on the level set picture? And this is another one of these kind of unsatisfying things. This is entirely within the domain. I can't see the target at all. I can't therefore actually even see the values of the function at all here. Right? I just pictures in the domain, that's it. So we know that when you have level sets, when you have a picture of level sets, you tend to draw several level sets. So each one of these curves here is intended to be a level set. And let me highlight just a couple of them. Oh gosh, now can I? Yeah, well, I've done worse. Let me try that first one again. Yeah, this is harder than it looks. Let's see, I think I can. Okay, good enough. Okay, so looking at this picture here, if I can, there we go. Is the partial derivative the slope of one of these lines? No. This is one of the standard common landmines that students step on. They see a picture, the picture has a curve. They remember from Calc 1 that derivatives are slopes of curves, and they think that, well, therefore, these, okay, fine, partial derivatives, must be somehow or another slopes of these curves, and they are absolutely not. It's not even close. So, again, be really, really careful. The reason you can't interpret partials as being slopes here is because this is not a graph. All that business about slopes is for graphs. So, okay, so what do we? How do we make sense out of this in this context? Let's imagine that these lines are contour lines on a like a map of a mountainous area. And we're thinking about how to climb this mountain. Y'all remember that metaphor. If I'm taking a partial with respect to x, that means I'm moving in the x direction. And notice I can get from the one contour line to the two lines over. As I go in the x direction, I gain these 200 feet of elevation over a very short distance. So this, if you will, fraction has a small denominator, which means that this is a relatively large fraction. Whereas, if you were to try to get from the lower altitude to the higher altitude in the y direction, takes a relatively longer distance to get from the same lower purple contour line to higher purple contour line. And so there is a relatively large denominator, if you will, and therefore this partial is relatively small. So, yeah, it's not slope. And it's also disappointing because, for one thing, I can't quantify. You notice I didn't say, again, geometrically exactly what are these partials on this picture. No, I can't, because I don't have scale. There's not indicated anywhere on this drawing which of these lines are how many feet apart, and how far is each one of these horizontal distances. What's the scale? I have no sense for that. Right? So you don't typically get actual explicit geometric interpretations. But roughly speaking, the faster you cut through contour lines, the larger the partial derivative is. Per this example. How are we doing? Is everybody on board? Okay. All right. Okay, if I can get this thing. Come on. There we go. Okay. All righty. Next thing, we're going to talk about linear approximations. Y'all will recall linear approximations from Calc 1. And I'll remind you of this formula right here from Calc 1. A lot of people mistakenly think this is a tangent line. It's not. Again, it's one of these sort of sloppinesses that you can get away with in a Calc 1 class, but not here. This is a function. Linear approximation describes a function. This is the linear approximation. The tangent line is the graph of this linear approximation. So try not to conflate those two things. Again, it's important to distinguish a function from the graph of the function. Okay, now that said, what is it that makes, how do we characterize this as being the linear approximation? And there's different ways to do this. My favorite is to observe that among functions whose graphs are lines, functions of this general structure, this is the only one that has the same value as f at the point A, and that furthermore also has the same derivative as f at the point A. There's always we're assuming here that this linear approximation exists. There's some formalities that we'll worry about later on. For the moment, I'm going to sweep under the rug. But assuming there is a linear approximation at all, there will always be exactly one function of this general structure that agrees with f in value and derivative at the point A. And it's not hard to confirm this, and I think this is a healthy exercise. Y'all should do this for yourselves. Make sure that you know how to prove that this function indeed has the same value and derivative. And of course, it's just a matter of plugging in. No big deal. The one little tricky, the one little possible point of confusion is that a lot of students will look at this factor right here and think that that's a function. It's easy to get. It looks like a function. It says f prime. Isn't f prime a function, right? But very importantly, no. We are plugging into that function a constant, fixed value a. And so even though f prime was a function, when you plug in a, this whole thing here becomes in fact just a constant. So taking a derivative of this L function is pretty straightforward. It's just a constant times x plus another constant. So with that in mind, easy to confirm. Make sure you can do that. Okay. Now, this was for a single variable function. What if we have a multivariable function? Let's do it like this. Multiple variables, multiple input variables. Now, still real valued. We'll worry about vector valued on the next page. So for the moment, let's not worry about that at all. So real valued, a single output coordinate, but it's a function of several inputs. I'm just going to throw the answer out here, and then I'll justify it momentarily. Here is the function that does what we want it to do. This is what we call the linear approximation of f at a given point A. And what do I mean by linear approximation? I mean the function of the basically pseudo-linear. It's what we call an affine function, right? But other than this constant, it's a linear function. Anyway, this is the unique such function that agrees with f in value and in derivative. Oh, wait a minute. There's multiple derivatives. Okay, it's got to agree with f in all of the partial derivatives. And assuming that such a function exists, there will always be exactly one. So notice how the strong analogy, right? These are the requirements that we had for a single variable linear approximation. These down here are the multivariable analog. It's the exact same idea of just, okay, we have to recognize there are multiple partials. So, okay, multiple such requirements. Everybody believe it? Everybody buy it? Seem reasonable? Now again, I'm gonna suggest the exercise. Make sure that you can do this. make sure that you can confirm, indeed, that this function satisfies these requirements. And again, it's just a matter of plugging in, pretty much. You do have to take a derivative of L at some point. And along those lines, let me remind you, just like in the above scenario, even though this thing here looks like a function, after all, it's a partial of a function. It seems like it ought to itself be a function. And it was until we plugged in a fixed constant value A. And when you plug in a constant value, then this becomes, well, in fact, just a constant. Weird constant, but constant. Is that cool? Yes.
Okay. So that means the partial derivative of f with respect to xn at a
yes.
Vector.
Yes.
Okay.
Yep. So this is what I'm claiming is a constant.
Is that bar just like the notation?
The bar just means evaluate the thing to the left at the point indicated at the bottom.
Okay.
Yeah,
is that the same as like on the page before when we just have like the parentheses like ABC?
Kind of. I mean, the reason I didn't use that notation here is because here's what I would have had to write if I wanted to use the more sort of normal notation. I would have had to say partial of f with respect to x in, at a, and then I would have another parentheses xn minus an, and it's like, I just think it's weird. It almost now looks like I'm multiplying these two parentheses together, which I'm not. And so this is fine. I just find this a little unsatisfying.
Yeah, I was just
trying
to understand what it meant.
Yeah. This right here is what that means.
Okay.
Yeah. Yep. Okay. Okay, so again, nice exercise. Confirm for yourselves that this function satisfies all of those rules. All right, now that said, this function's a little bulky, clunky. It's a lot to write down. And so I'm going to shorten it by making a convenient observation. Let's look at these terms right here. This is almost the entire function. This is not, of course, the f of a at the beginning. That's not included. But just the remaining terms. It's a sum of a bunch of products. And a good general, strategic, point of view to always be on the lookout. Whenever you see a sum of a bunch of products, it might make sense to either recognize it or choose to view it as being a dot product. After all, a dot product is a sum of a bunch of products. Right? So I'm going to choose to view this as being a dot product. And now, what is it that I'm taking a dot product of? Well, if I look at these, what you might call the second factor in each of the products, that second factor, those are literally the coordinates of the vector x minus a. That's exactly what its coordinates are. So cool. So this is starting to look a lot like a dot product. Now there are these other factors here. What are we going to do with these things? Do we know a vector at this point whose coordinates are the various partial derivatives of f? Not really, right? That's not an existing previous thing that we'd already set up. So I'm going to choose to define such a thing. This thing is called the gradient of the function f. We use this notation right there. Do be careful, please. This little triangle that we use to denote this, that is very importantly, the point points down. If you have the point pointing up, it actually means something different. There's another mathematical expression where the little corner, the pokey point is actually up instead of down. So do make sure that this is pointing down. It's called the gradient. And so with that in mind, This expression that we had up here, this great big tedious bulky expression, now is just this dot product, and much more convenient to write it like that. How we doing? Everybody okay? Any questions? Okay, so in practice, day in and day out, this is how we're going to write linear approximations most of the time for multivariable functions, real valued multivariable functions. Okay, let's see an example real quick. This is a very plug and chug kind of a question, so I want to know what is the linear approximation for this function evaluated at this point. I'm literally just going to copy. So the first step, apparently I need to compute f of a. All right, well, here's our point A that we need to plug into this function f. And so plugging in this point into that function gives us some arithmetic, which turns out to be 5. Easy arithmetic, right? Hope that makes sense to everybody who's plugging those numbers. X is 1, Y is 2. Boom, the value's 5. Okay. All right. Next, we need to know, apparently, the gradient of f evaluated at the point A. Okay, let's slow it down. Let's first talk about just the gradient of f itself. The gradient of f is a vector whose coordinates are these various partials. So one step at a time, let's just compute these partials. Now again, I'm going to assume that y'all are going to take the time necessary to get good at computing partial derivatives. Nothing to it. Each one of these partials, of course, assumes that the other variable is constant, and thus these answers. Make sure you're good with this. Okay, so that's our gradient of f. Now we need to evaluate that at the point A. So I've got to take this point A and plug in to those functions, all together then giving me the numbers 2 and 4. Right? When you plug in x equals 1, y equals 2 into the gradient, you get 2, 4. And that goes there. Everybody good? Okay. Okay, let's see here. Yeah, okay, then last, x minus a. Well, I mean, this is kind of the easy part. A is given, 1, 2. The x vector, let's see here. I'll use, fine. The x vector, of course, just has coordinates x and y. And so x minus a is there. Everybody happy with all of that? Very plug and chug. Oops. Now, if you like, I suppose you could dot out this dot product and kind of collect some terms and move things around. If you're so inclined, I don't think that's particularly worth it in a context like this because that's trivial algebra, and at the same time, this has some advantages. This form up here, I can see what the gradient worked out to be. I can see explicitly how the 0.12 is showing up. I can explicitly see what the value of the function at A is. I like being able to see useful information. I think there's a tremendous value in leaving it in that form. But outside of this class, I mean, at some point, if you're going to be coding this into a computer and it has to compute a couple trillion values of this, yeah, sure, streamline it. Go ahead. I suppose in that context it makes sense. But most of the time I'll just leave it like that. Okay. Okay. So, reminder, we started off with real valued single variable. We then moved on to talk about real-valued multivariable. Now the natural next question is, what if I have multiple output values? In other words, what if I have a vector-valued multivariable function. How do we make this work? How do I do a linear approximation? And now I'm going to present this in a different order. You'll notice the first thing I did in this case was to write down the function, and then I introduced the necessary shorthand to rewrite that after I had written down the function in the fully expanded, fully clunky initial form. If I do that for the vector valued case, the vector valued analog of this is just it's way too many terms, and there's just kind of no point. So I'm going to give you the shorthand notation first, and then I'm just going to write down the shorthanded answer to save us that little bit of pain. So here it is. This is the notational convenience we need. This thing here called df. This is a matrix, as you can see. It's going to turn out this will be exactly the little shorthand that we'll need to make this all work. Notice that it's made up of a bunch of partials. Notice that in the first column, all of the partials are with respect to x1. I think it's reasonable then to call this the x1 column, because this is the column where the input variable x1 is relevant, and it's the only column where the x1 variable is relevant. Likewise, x2, etc. Lastly, in the last column, this is where your partials with respect to xn go. So one of the big important factors to keep in mind about how this df matrix is structured is that columns correspond to input variables. Really important to make sure to keep that straight. Okay, next, let me point out this row. We're taking partial with respect to f1 for all of the partials in this row. So I think it's reasonable to call this the f1 row. And then likewise, this last row is the fm row. Notice then all of the rows correspond to output variables. Right? So if I say this is the matrix where I take the partials of all of the outputs with respect to all of the inputs, it is what it is, right? But organized specifically in this way. Columns correspond to inputs, rows correspond to outputs. And by the way, make sure not to accidentally transpose it. That's importantly, you get catastrophically wrong answers if you accidentally transpose it. Okay, so with that in mind, this great big monstrosity of a shorthand called the df matrix having been established, here's the formula for our linear approximation for a vector-valued multivariable function. Right? Notice that df is playing the role that the gradient did for the real valued case, which itself was playing the role that the regular old derivative did in the single variable case. Right? So remember what I said at the start of today's class and the end of last class, that there's various different kinds of derivatives. A lot of people, based on only this that we're seeing here, a lot of people would make a very reasonable case that for a multivariable function, the gradient, because it plays the role that the derivative did in Calc 1, a lot of people would call this the derivative of the real valued multivariable function. And likewise, a lot of people, myself included, would point out that because this monstrosity here is playing the role of the derivative in the linear approximation formula, a lot of people would call this matrix the derivative of a vector valued multivariable function. Again, I think that's a really good point of view. And there are better reasons than this as well to call this matrix here the derivative. So again, real quick, we'll see an example here. This is also very plug and chug. It's just a matter of doing. Reminder, I got ahead of myself. Make sure to check these conditions. Again, very analogous to what I've already suggested. But do make sure to check that. And this, again, is very plug and chug here. You take the appropriate partials. We take the x partials, put them there. We take the y partials, put them there. All right, that gives us our DF matrix. We plug in the point by plugging into that matrix. That then all together is our DF matrix for our linear approximation, and everything else is just a matter of writing it down. Okay, and I bet you we're out of time by now, so yeah. Okay, there we go. Okay, so y'all have a good rest of your Wednesday. See you on Friday. We'll draw a line right here.